Alright, welcome back to learnpiezo.org or .com and Ultrasonic Advisors, kind of merging these two platforms and making them into one with a common goal. But here we're going to talk about FEA programs, finite element analysis, with regards to piezoelectric devices. And finite element analysis, as many of you are aware, is a way to simulate sort of complex or non-standard, so complex geometry. Devices, and it allows you to quickly and easily gain insight into the design and performance of your device. So what we want to do is talk about the different commercial offerings or platforms that are used to simulate piezoelectric devices. And I will list here the ones I have experience with in the order that I have experience with them. So amongst the tools that I've used, the software tools, I have used Comsol, Ansys, something called Attila GID, and I've also used sort of your specific package, like your specific CAD package. So there's CAD package simulations. So this could be your SolidWorks, this could be your Inventor. I've used all of these. I haven't used CAD simulation packages as much, simply because I've had, these other packages offered, or I've had access to them at different points. So I haven't really delved a whole lot into CAD simulation, but this could be important and for certain applications, for certain people, depending on what software offerings you have. So I'm going to talk about these 4 different types of methods to simulate piezoelectric devices, and what's kind of the benefits that I see, and what are the disbenefits of each of them. So first, I'm going to compare two very sort of commonly compared packages. That's Comsol and Ansys. And both of these have, obviously, all the packages have good implementation of piezoelectric physics. That's electrostatics, that's transfer from mechanical energy to electrical energy. They all have that. It all should work very well. But then there's that next level of how well can I get it to work for me, and what are the challenges and what are the differences between each of these programs. And I will be easily able to talk about both of these. So let's start with Comsol. So Comsol has a good way, very good with material properties. You can put your equations both in, you could say, the piezoelectric D constant or the E constant method. So you have your choice of what kind of material properties are put in. The D constant and the elastic constants according to open or close short circuit conditions. This will be so much easier to deal with than having to convert your material properties into E constant, which some programs make you do. So this is great for modeling loss mechanisms. So that's the quality factor, that's your dielectric loss, tangent delta. What this program does is it gives you, like, for example, it'll give you S prime and S double prime, so it'll allow these the ratio between these two factors to then determine your quality factor, or if you're going to be doing permittivity, prime, this is constant stress, S double prime, or you can say T. I think that's another common one. I think that's the most common one. So basically that ratio is they're going to determine your tangent delta, and I have other videos on how these are related. It's just a ratio, inverse ratio, actually, inverse. So that is not the way traditionally things are done. Usually you put in your real property, which is here, and then you put in your tangent delta, but that's okay. I don't think that's too confusing. So the other thing in Comsol, it doesn't calculate impedance or admittance for you right off the bat, or phase. You have to put those equations in. But the way to put those equations in, I have a couple videos on Comsol. If you look up Comsol Learn Piezo or Comsol FEA, piezoelectric, I'll be one of the first videos on YouTube. But for Learn Piezo, but you have to, for example, in order to determine the impedance or the admittance for that fact and the phase, you'll have to first sum the charges using a probe, sum charges. Then you'll have to multiply by omega in order to get the current. In order to get the absolute impedance, you have to then take the voltage, the absolute value of the voltage, and the absolute value of the current. And that gives you your impedance. So that is what ends up happening. And in order to get phase, you're going to have to do, you're going to do the imaginary, or actually it's the real, over the imaginary impedance. So you put that equation instead of doing absolute, you just do real and imaginary. And that would then give you your ratio. And I go over that in one of the videos. So you have to do some math, and I think you can just do this with the current. But you're going to have to do some math in order to get phase, voltage. Well, voltage should be easily calculated, but using a charge probe, and you're going to have to put your electrodes in like normal. It's not too complicated, but there is a little bit of math. You shouldn't be afraid of this level of math, although it's not like plug and play. Let's check Ansys. So Ansys, yeah, it does piezo simulations, you know the static, the frequency response. It does the modal analysis. Material properties, I do not like the way they put material properties in. I don't like it. So there's like going to be one screen for your elastic properties, and there's going to be another screen for your like dielectric properties. And there's going to be, I think, another area where you put your piezoelectric E constant. You cannot do D constant. So you don't have the flexibility of putting your material properties in the way you want. Now, this is a huge oversight, and this completely highlights the fact that in Ansys, piezo is an afterthought. And it's an add-in. In Comsol, it's not an add-in. It is part of it. It is integrated. It is part of. It is just like any other solver or material type. It's not like a mechanical FEA program with piezoelectric. It is a multi-physics kind of basis. So and Ansys has has a long history. And that history kind of bites itself in the butt sometimes, or it becomes inconvenient, not user-friendly, awkward. But anyways, if you have a lot of experience with Ansys, then you will be able to get piezoelectric materials to work for you. But starting off the bat, choosing which platform you want to use. I'm talking about Ansys Workbench here. It is not convenient. The way to put in losses, also, in order to do this, you have to have like a Excel worksheet. Now that is getting too many complications in order to put material properties in something so simple. I'm not talking about calculating phase or other types of material things. I'm talking about very basic material properties, and this is actually very basic math that it really makes sense to me. It won't make sense to everybody at first, but it's something you should be learning, and it will only take about 30 minutes, 10 minutes to learn, and I have it all very clearly laid out in my Comsol tutorial. But funny thing, I don't have access to it right now, but I did in the past, and I liked it. So continuing on, Ansys, this you're gonna have to, in order to get this to work properly. So there's ways to put damping in Ansys, but it's not really good. I don't like it the natural way. There's also you can put in a command, because Ansys has a history of kind of working with commands, and that's kind of how it got originally started, with a very kind of not user friendly, not graphical interface, very heavy interface. So it kind of have its, I think it's called ADPL code, ADPL. All right, I don't know what that stands for, but Ansys, I don't know what it works for. But basically you have to put in like a command, which I don't like, where you have to go around the standard way of making. It's not hard to put it in, but to put in the loss factor or the command for that, but it's not. Oh man, it's not something I think we should be doing. Jumping. We should have a choice basically of which kind of material property choice we want to put in. We should also not have to use an Excel worksheet with matrix inversions, and then even on top of these matrix inversions, the method for inputting material properties is still not a standard method. It is the Ansys matrix. So that's not right. You shouldn't make your program so specific that it becomes an Ansys method of putting it in. Not even a standard strain form of the equations. All right. Next part. So the ADPL code, this part is a little bit better. Calculating the impedance and admittance is something that's very common for piezoelectrics. Obviously modal analysis and static are kind of more straightforward. So I'm talking about frequency response here. So here we go. There is the add-in has calculations for this. You can automatically calculate it. Because it's an add-in, it doesn't always play nice, but it does play. Play nice, but it works. I've used it. It works. You can't do in order to do like calculations, it's not very convenient, and to come up with different ways of manipulating your parameters. Comsol really has a nice integrated way of doing that property manipulation if you want to come up with any different type of quantity, but Ansys does not. So you're gonna have to do some coding. So you can get these plot within the Ansys. You can export the data, and the export, for some reason, it gives you real and imaginary impedance. So I'm not a fan of like how it shows it in one format. In Ansys, it shows it like this, but then when you export it, you get real and you get imaginary data. So you could obviously calculate it using Excel. It's not difficult, but it's like what's going on here? It's not streamlined. So I'm as you can kind of see, I'm not very impressed by Ansys's implementation of piezoelectricity. I think at the core of it, both of these methods will work, and you can get them to do the exact same thing. But the user interface of Comsol is so much better, so much more integrated for piezos than it is for than Ansys. It really feels like you're using a add-in. No, Ansys may be awesome at other things. You may want it to integrate to other types of simulations, which it is great for, but it is not the starting choice for a piezoelectric simulation. Unless that's something that's already available to you, then obviously weighing in the choice of buying a completely new software, learning how to use that, and all the different quirks about it, which there always is quirks about software simulation tools. At that point, if you're starting fresh, I would just definitely choose Comsol, especially if you want multi-physics capabilities. Now we'll go into our other choice, which is Attila GID. So this program is a dedicated to piezos. That means your material properties are done properly. And that means your calculation of things like impedance or admittance and the phases are already done for you. This program is supported by a lot smaller company. So it's a smaller company. So it doesn't have the feature richness of Comsol or Ansys, right? It doesn't have the feature richness of Comsol or Ansys. That's obvious, okay. But it is dedicated, and there's always so much benefit in dedicated tools that you know are doing the calculations and measurements correctly. So if you're going for a CFD coupled with piezo, which would be an enormous simulation anyway in your Ansys or Comsol, then you can never do that. But acoustics, either that's in water or if that's in air or another different medium, and piezo, that is something that is commonly utilized in this program. So this program has a lot of documentation around different applications, and you're not going to find that with Comsol or Ansys because piezos aren't the heavy users per se. They're used by a lot of different companies and components, so you're not going to be finding as much support. And that's where I think this shines. It shines in helping the customer get this implemented. So helping customer. With Comsol and Ansys, you won't get very good support. You'll find companies trying to support you with these products, and they will not do a good job because they don't have both experimental and they don't have both simulation and experience. Many companies doing this sort of work with Ansys and Comsol, especially with Ansys, have very poor. I have had very poor experience with external kind of people who are selling you Ansys and also doing consulting with it. They're not very good with the piezoelectric part. It's not complicated, but it's not directly simple and doesn't relate to. And there's not a lot of documentation around it. There are some example files, but I don't think they're kind of not sufficient especially when somebody's getting started. And knowing how to interpret results. However, Attila is supported by a smaller company which focuses on piezos, on design and test of ultrasonic devices, so you will be able to get the support you need to have a successful simulation and understand some of the design criteria and getting going. You really are, it has the benefit of being dedicated to piezos. you will get the support you need to perform frequency simulations. Static, obviously, and modal are simple, but it doesn't have complicated, not complicated, but it doesn't have all of the multiphysics tools that other components have, like CFD. You can never couple a CFD. You can, but it's not something you would normally want to do. Couple that with Attila, you'd have to use other programs to link that in. But you can do it. I mean, I don't know, but it may be possible. But however, acoustics and piezos are very well integrated together. And although there's other things related to energy harvesting, and a lot of other convenience features, like you can attach it to external circuits. Other convenience features of this include a really good one. Oh, I love this feature, and that is the coupling factor. So the coupling factor is a measure of how well the piezos are coupled to a specific resonant mode. And typically the way that could be calculated is that you have to perform a frequency analysis where you get your impedance, and then you look at your resonance and anti-resonance separation. You calculate a coupling factor in terms of percentages. Well, this program will give you, when you do modal analysis, so let's say this is n is mode number, and then so you'll have, like, let's say the mode number 1, frequency 23.1 kilohertz, the coupling factor is 1%. And then you have mode number 2, 25.9 kilohertz, and the coupling factor is 20%. So hey, this is actually a mode that couples well. Let me go investigate it. Instead of providing an entire frequency response, you'll actually understand which modes are excited more, and that'll more easily allow you to narrow in. So it's helpful in that way. But for extremely large simulations, this would be a difficult choice. But for things like ultrasonic transducer design, especially, my experience has been in, power ultrasonics, not necessarily, not diagnostics. So I can't speak to that, but I imagine this may be more difficult to model diagnostics, just because of the sheer amount of solving power and flexibility needed. But I know personally for design of ultrasonic transducers which operate in a steady state mode, for which frequency analysis would be good, for which modal analysis would be important, this would be a powerful choice. And you can also get a free trial of all of these programs, Ansys, Comsol, whatever, that all of them work with those free trials, and if you contact the companies. So finally, what I want to introduce, and I think I forgot to mention earlier, is a program called OnScale. So OnScale is completely on a different category. Maybe I should use a different color then. I'll use orange. So OnScale is on a different category. It only does transient simulations, but through FFT, it allows you to get frequency response type of information. That's Omega right there. It only works on the cloud. All of these other programs, they work on your desktop, and they solve using your desktops or your laptops computing power. This uses the cloud computing power. This is pay as you go, so you pay for sort of the computing power go. And so so it does a good job with material properties, because it's actually dedicated for piezo's as well, or dedicated for this type of work. So it does a good job with material properties. What was the other categories? it will do your impedance for you and all the other things. So that works out well because it's a dedicated solver. There's no need for absolute value there. But it is, I think it's right now at this point in its stage in development, it's a little bit awkward for frequency analysis. It's very well suited for transient, which means diagnostics. I think it's probably going to be the best, especially in the computing power needed for a diagnostic, sort of transient. And when I mean diagnostic, I mean like pulse echo, echo, receive. I'm talking about like NDT, non-destructive testing. I'm talking about medical diagnostics, like ultrasound. This would be the program of choice simply because it works, it performs these tasks well, and it also has cloud computing power, which can be very important in order to complete those simulations with the appropriate amount of refinement and trust in the data. But I haven't found it to be useful for frequency analysis at this point. It can be used, but and there are methods of doing it, and there are some explanations about how, but you'll find in all of their examples, they will not, for example, simulate a welding transducer. Or they won't simulate an ultrasonic cleaning transducer, or they won't simulate other types of horns, like let's say any ultrasonic device with a horn on it, or it does static simulations too. But these sort of ultrasonic ones, were kind of below 200 kilohertz, they won't show that, and the reason because it's I think it's not very well suited for it. It's better for diagnostic, what I call diagnostic, which is like NDT, medical ultrasound, pulse echo type of simulations. So I'll kind of put this in perspective now. Let's change colors here. So Ansys. So it has multiphysics very well, but it is awkward. Mind you, all of these work. The next choice is Comsol. It does multiphysics. A little bit amount of custom work needed. There's some custom work needed, and actually overall I like it a lot. I like this. Then there's Attila GID, and I believe where this really shines, it does acoustics. It doesn't do complete multiphysics, but it does acoustics. Obviously electrostatics, which is necessary for piezos, that's not an option. But it is piezo specific, and that's where it shines. So if you are mainly working on a piezoelectric device, then you have this as an option to explore and try, and you'll have great support. It's supported by a smaller company which does this for a living, you could say, and I think you will have success with this program if you deem that it provides the capabilities that you want, then it will be successful for you. And remember, with simulations, you want to go as simple as possible. You don't want to make things as complicated as possible. So despite maybe you can say some of the limited factors in multiphysics, you may say that you have your piezoelectric device interacting with the fluid and you want to model all of that. Well, it's, in my opinion at this point, I feel like it's not very likely you'll get a lot of benefit from from hooking those two things together. You could use still Comsol or something else for a CFD, which you might already have, but hooking them together, it's going to be tough to get results that mean anything, or have that level of that you can actually interpret to the extent that you simulated it. All right, and it's going to cause a lot of computing issues too with how much memory it takes. So now what's the next guy? The next one is this is acoustics too. The next one is oh, I think I forgot to mention one of these. So I'll do on shape, or sorry, on scale. It does well with visual properties, but it's pretty well suited for transient simulations only. And it's pay as you go, which is way different than the others. And all of these are desktop solvers. They all do transient. All of these do transient too, but this is like a dedicated transient, so that helps there. So finally the issue I forgot to talk about was your CAD packages, your CAD package simulations, and these give you a lot of bang for your buck. These are really cost effective. You likely already have them. So they'll definitely have modal analysis. You can do static, but not really. You can't put anisotropic material properties. It's not a game. It's not a deal breaker. Some of them have frequency response. Not all of them, but some of them have frequency response, and this is where the gold is here. If you can have a program with frequency response, if you have let's say you have a transducer, and let's say this is these are two piezoelectric ceramics. This is your horn, and this is your back mass here, and your little nut there with your bolt going through. So if you apply on this surface force going that way, and on this surface force going that way, and you have some sinusoidal function here, and you have some amplitude of your force, then you will effectively have piezoelectric forcing. So you'll be able to tell what frequencies are simulated the best by your piezo, because that's the way of simulating. So it is also very possible to make these CAD program work. You're not going to be caring about material properties as much for the piezo, and the way you put it in, the way you put losses in. You're just kind of looking for a general analysis, and you're not going to have your impedance at all. Probably you can calculate it, and I may show in a future video how to do that, but it's going to be a general analysis tool. And you may say, oh wow, this is general, but so it's going to be a general analysis tool to begin your experiments. So that is very important here. What your FEA program is not supposed to design your entire device for you. It's supposed to get you to the point where you want to do experiments. Because really, when you start your experiments, that's where many of the problems lie. When you find problems in experiments, then you look for FEA to solve. So the FEA is not going to provide you your final device right off the bat. It's my way, and the way I would do it, the way I do it, is you use FEA to come up with your first prototype, your first idea, so you're not completely just drawing out what you think, or 100% relying on predicate devices or just equations. You would first just make sure nominally the device works as intended, and once you can understand that it works as intended, then you go ahead and produce the experiment. You produce the device. If you find it not working, use FEA to understand why it's not working, and experiments obviously. And then after you have found a working device, you can go back to FEA and then further optimize it. So in this case, if we want to add this now to this list, so let's say CAD sim, it's just for the cost is down. I think because you already probably have something similar to it, or you can purchase it, something like Inventor. The simulation on that package is less than $3,000 a year, which is probably the cheapest one. You also get a prime CAD package out of it, but if you already have a CAD package, you just may want to add that capability. And these CAD simulations will also have, I don't think they'll have very good multi-physics capability, but you can analyze each portion of the analysis independently. Like you could do you could do CFD. You could, like, for example, say how much displacement you're getting, or give an estimate, then do CFD after that. It's not a complete A to Z simulation, but it's an A to B, then it's a B to C type of thing, or A to B, then a C to D. So you got to fill in the B to C yourself. So just as good for general analysis, and it is a perfectly acceptable option. It is perfectly acceptable to do this way. So I've had experience using all of these. The least experience I've had is probably with OnScale, but I think I gave it kind of understood what it could do, what it can't do by by the tutorials they gave, and by by my own a little small amount of work trying to simulate a piezoelectric device, and also communicating with their technical staff about simulations. So it's very powerful, but it's not yet, and I understand there's some development going on, but it's not yet a tool to understand the behavior of steady state operated devices. Alright, thanks for watching this video on FEA in piezoelectrics.